Now let's understand the kernel trick. If you remember the equation, this equation, right, we said that we are going to solve it using something called Lagrangian multiplier, and you will see it in the resources. After solving the Lagrangian optimization problem, we will have something like this, right? This is the equation we will have. It's a minimization equation, so we want to minimize alpha. You can see that we don't really have w's anymore in the equation, right? We have only alpha, so we want to optimize or minimize alpha. And in order to minimize alpha, this is the equation we have. We have negative summation of alphas, and then plus half summation of n and summation of n also. But as you can see here, we have ij and ij, right? And here we have xi and xj. So what all this? Here you need to understand that this notation, right? If we write notation like this, then this is called the dot product between two examples. Okay, so this is the first example and this is the second example. We take the dot product between them, and the dot product is something from the linear algebra. We don't really care about this for now. Okay, and these are the constraints we have for this optimization problem. We also don't care about this, and alpha is basically a slack variable. What are the other slack variables we introduced before? We introduced eta, right? So slack variable is something we can introduce to solve a specific problem in our optimization. Okay, so now, as we said, we are optimizing this equation. We either minimizing this equation, right? So minimizing negative and plus. If we have it the other way around, right? If we multiply all this by -1, then this is a maximization problem, and we want to maximize this term minus this term, right? Instead of minus this term plus this term. Okay, so as we said, we have two constraints. The first constraint is that this variable, this alpha variable, cannot be negative, so we need to have for all i's, right? For each I, for each example, we need to have alpha bigger than or equal to 0. So we cannot have the weights, the new weights we have right now, instead of w's, we have alphas, right? They cannot be negative. This is the first constraint. And the second constraint is that alpha times I, the summation of all this, should be equal to 0, right? These are the two constraints we have for our optimization problem. We don't really care about this right now. This is all the mathematics you can see in the resources, but I'm just explaining what's happening in general terms. Okay, so here we are saying ui and uj. So what is ui and what is uj? As you can see here, points with different labels increase the sum, while points with different label decrease the sum. So as you can see here, points with different labels increase the sum, right? And points with the same label will decrease the sum, right? Because here we have negative. Okay, so if we have different labels, if we have 1 and -1, the two labels we have are 1 or -1. So if we have two examples, the first example has 1 and the second example has -1 as a label, or the other way around, then the multiplication between 1 and -1 will be -1 times -1, it will be 1, right? So it will increase the sum. But if we have the same label, so 1 multiplied by 1 is 1, right? So it will be -1 because we have a negative here. Or the other way around, if we have -1 and -1, if we multiply them together, it will be 1 also, right? So points with different labels increase the sum, while points with the same label decrease the sum. Okay, all this is not important. What we really care about is this part, right? This measures the similarity between points, right? xi, xj. So we said that this is called the dot product. You need to understand that the dot product, it's a linear algebra terminology, but it's basically also used for measuring the similarity between the points. Okay, so this measures the similarity between the points. Now, let's introduce the kernel trick. So this is the equation. We don't really understand what is happening here, right? This is the SVM equation, and this is for measuring the similarity. Okay, now let's understand the kernel trick. Let's look at this graph. This is the original data, right? And we have two classes as usual. So we have this red and this green and this green, right? So we have two classes, and of course, if you think about the decision boundary here, it's a nonlinear decision boundary. So if we want to have a linear separator or a linear hyperplane to separate the data points or separate the classes, we cannot do so using this space, right? So how we can solve this problem? Imagine that we have a function, right? Some function, and this function will map the data into another space. This is the idea of the kernel, right? So it will take the points, and when we multiply or whatever the function that we use, it's called a radial function, and we will see what we mean exactly by this when we discuss the kernel types. But basically, the radial function will take these data points and map the data points into the new feature space, and in the new feature space, as you can see, the red points are close to each other and the green points are close to each other, so we can separate them using a linear separator, right? So this is the function that we use to map the feature space, right? Now, the function we want to optimize here, we cannot really optimize this, right? And we cannot optimize this, we cannot do anything for any of these parts. But what we want to optimize is basically the dot product of the two feature vectors, right? So we have the first feature vector and the second feature vector, and we want to optimize this feature vector, okay? Now, if we transform, right, if we transform using this function, instead of computing this dot product, right, so we have this dot product, we said that the dot product is xi times xj, right, here. Now, we will have to compute phi of xi times phi of xj. So we will apply the transformation function on xi, and we will apply the transformation function on xj, and then we will compute the dot product between this number after transforming and this number or this vector after transforming, right? The problem now is that this is expensive and time consuming. You need to compute the function for xi and compute the function for xj, and then compute the dot product between them, right, in order to apply this function, okay? Now, this is expensive and time consuming, and we will see an example in a future lesson, okay? Now, we have a kernel function, right? If we have a kernel function just like this, right, k of xi and xj, it's just, as we said here, it's phi of xi times phi of xj, okay? We don't really need to know or compute phi at all, right? We don't really need to compute phi at all. The kernel function defines inner product in the transformed space, or basically this kernel function will define the similarity in the transformed space. So we said before that the dot product, right, the idea of the dot product is measuring the similarity. Now, the kernel itself is measuring the similarity, right? It defines the similarity in the transformed space, okay? So using this trick, this kernel trick, instead of this function, right, instead of this function right here, and instead of computing phi each single time or computing the transformation function each single time, we will compute this equation, right? So as you can see, kernel of xi xj. So what will happen is that we are going to compute xi xj just like before. So this is a given. We cannot really decrease this part or remove this part, right? So we will compute this part just like before, like any machine learning algorithm. We will compute the dot product between this and this, right? And after we compute the dot product between them, we will just see what the value should be in the kernel, okay? So this will happen. So this is basically what happens using the kernel trick, okay? We don't really need to compute phi of xi and then phi of xj and then compute the dot product between them. This is very, very consuming and time expensive, okay? So let's take a look at a kernel trick example. So let's see, without using the kernel trick, using this trick, what we needed to do, and now what we need to do, right? Let's say that the kernel we are using is a polynomial kernel. So we used the polynomial kernel before, right? Here, if you remember, we used a polynomial kernel right here, right? So this is a polynomial kernel. We just took the function, right, and we squared this and we squared this. So this is a polynomial. Now let's have a more generic approach or a general function for the polynomial, right? So we have here xi, xj, this is what we were calculating before, plus 1. So let's just say that this one is for the bias or whatever, and we have power p, right? So this is the kernel we are going to compute. Now b can be 1, 2, 3, whatever. Now evaluating k, in order to evaluate the kernel, right, or evaluating the values in the new transformed space, we need to just do this, right? We were doing this before, right? The original dot product. This is, as we said, we cannot really remove it or decrease it or get rid of it, right? So what we need to do right now is one additional addition here, right, and one additional exponentiation. So this will be computed. We will have some number here, and then we will add 1 to this number, okay? And then we will take this number. Let's say that this number now is 4. So 4 plus 1 is 5. And then let's say p equal 2. So it will be 5 power 2. It's now 25, right? So we didn't really need to do any extra steps or any extra calculations other than one addition and one exponentiation. So this is the kernel trick. Before, we would have needed to compute the transformation for xi, right? Apply this kernel on xi itself, and then apply it on xj itself, and then perform the dot product between them, and this will take so much time, right? So this is the kernel trick. We will understand more and more what do we mean exactly by the kernel trick in the next lessons, when we see the kernel types, when we see more examples, when we see the code, and so on. So if you still not sure what do we mean exactly by the kernel trick, don't worry, it's a little bit complicated, but it will be more clear in the next lessons. So let's go and understand the kernel types and see the different kernel types. So let's go.